This is the user interface of SimuLoop. SimuLoop is a PID loop simulator. It simulates a PID controller that controls a first order, second order, or integrating process in real time. You can switch between manual and automatic modes, and adjust the tuning parameters in real time. Before showing how to use the software, I want to show the different parts of this user interface. On the top left corner of the screen, we have two buttons to start and stop the simulation. Below that, we have the buttons to switch the controller between manual and automatic modes. You can see how the control mode indicator changes as I changed modes between manual and automatic. Then we have the setpoint control. We use this to enter a new setpoint to the system. We enter a setpoint by using this slider or by directly entering a value in this input field. Then we have here the manual output control. We use this to adjust the value of the PID controller output between 0 and 100% when the controller is in manual mode. Then we have the input fields to enter the PID tuning constants, proportional, integral, and derivative constants, and the output bias. On the right side we have the status indicator that tells us if the simulation is running or not. Then we have the data logging status that indicates when the system is recording data. Under the configuration panel, we have a summary of the configuration settings of the PID controller and the process. These configuration settings that we see here correspond to the default settings. And below we have the real-time monitor, which shows some real-time values of the simulation. On the right side of the screen, we have two real-time charts. The chart at the top shows the real-time values of the process variable and the setpoint values. Those values are displayed in the custom engineering units that you enter in the settings. The chart at the bottom shows the real-time values of the PID output and the manual output control value. These two values are shown in percentage units, 0 to 100%. The software comes with a first-order process configured by default, along with some PID tuning constants to control the process, so you can start running the simulation without having to enter any previous setting. I just need to click on Run, and the simulation starts running. Now I am going to make a setpoint change. The yellow line is the setpoint value, and the red line is the process variable. We can see now that the process variable is moving towards the setpoint according to the dynamics of the process that is configured by default. Let's wait for the process variable to settle at the setpoint value. Now that the process variable has settled at the setpoint value, let's make another setpoint change. Now we can see the process variable moving towards the new setpoint. Let's wait for the process variable to settle at the setpoint. As we can see, the PID controller is working as expected. It adjusts the output of the process in order to drive the process variable to the set point. If you ever need to return to the default values, just click on Configuration and then select Reset to Default. This was an overview of the software and the default PID settings and process dynamics that are configured in the software. Let's now see how to configure a custom process with different dynamic parameters and how to configure the PID controller. But before doing that, I will spend some minutes reviewing the main parts of a PID control system. In a PID loop, we have two main components, the PID controller and the process we want to control. Well, we need to configure both of these components in SimuLoop before we can run the simulation. We are going to start by configuring the process. The process has an input value that is expressed in percentage, from 0 to 100%. That input is generally driven by the output of a PID controller via an actuator. For example, the PID output might drive the opening of a control valve from 0 to 100%, and this valve may regulate, for example, the flow of gas into a furnace. So, as the PID output changes between 0 and 100%, it further opens or closes the valve, allowing more or less gas into the furnace, which in turn increases or decreases the temperature of the furnace. The output of the process is the variable we want to control. For example, the temperature of the oven. This output of the process is called process variable, or PV, and is normally expressed in engineering units, for examples, Celsius degrees. For this example, we are going to configure a first-order process, so when the input of the process is 0%, the temperature of the oven would settle at 25 Celsius, and when the input of the process is 100%, the temperature of the oven will settle at 300 Celsius. So, the maximum and minimum values in engineering units of the output of the process will be 25 Celsius and 300 Celsius respectively. As part of the dynamics of a first-order process, we also need to configure the time constant and the dead time of the process. When we change the input of the process to a new value, the output does not reach a new temperature immediately. It takes some time to settle at a new temperature, as we can see in the graphic. The time constant of the process determines how fast or how slow the process is. The higher the time constant, the longer it will take for the process to settle to the final value. For this example, I will use a time constant of 5 seconds. Usually, temperature processes have time constants much higher than this, in the order of several minutes or even hours. But for the sake of the example, we will use a short value. And we will use a dead time of 2.5 seconds. The dead time is the time it takes for the process to start responding after we make a change in the input. For example, if the gas valve is far away from the oven, when we change the opening of the valve, the temperature may take some time to start moving to the new value because the increased volume of gas needs time to reach the oven. In the image, you can see that the input of the process changes at time equals 0. However, the temperature does not start moving at time equals 0. It takes some time before the temperature starts moving towards the new value. This time it takes for the temperature to start moving is the dead time of the process. So, let's configure this process in SimuLoop. We need to click on Configuration and then on Process Dynamics. Here we select the type of process we want, in this case, first-order process. We select a maximum value of 300, a minimum value of 25, a time constant of 5 seconds, and a dead time of 2.5 seconds. Let's make sure we select direct action for this process. This means that the output of the process has to move in the same direction as the input. Now we just need to click on Accept. Now we will proceed to configure the PID controller. We click on Configuration and then click on PID controller. We need to select the PID equation we want to use. In this example, we will use the parallel PID equation, which is the one that is most common in textbooks. Since we will not use derivative action, then it does not matter what we select for derivative source. The control action is very important. It has to be the opposite of the action of the process. When we configured the process, we selected direct action for the process. Therefore, we need to select reverse action for the PID controller. The control action of the PID controller has to be the opposite of the action of the process. Otherwise, the control loop will not achieve negative feedback and will not be able to control the process. In the Tuning Units tab, we choose the units of the PID constants. I am going to leave the default tuning units. Now we need to configure the process variable limits of the PID controller. This setting is very important if we want to be able to control the process in all its range. The maximum and minimum values of the process was from 25 to 300 Celsius. I am going to enter the same limits for the PID controller. Now we click on Accept. The process and the PID controller are configured now. Let's do some initial testing of the process. We are going to test the maximum and minimum values of the process. If we want to test the process, we need to place the system in manual mode. Let's go back to this image to explain the difference between manual and automatic modes. In manual mode, we can adjust directly the PID output, which in turn controls the input of the process. We use the manual output control in SimuLoop to directly adjust the output of the controller. So, we can apply different input values to the process and observe how the output of the process reacts to these changes. As you can see, in manual mode the controller ignores the set point value. On the other hand, in automatic mode, the PID controller adjusts the output to maintain the process variable at the desired set point value. We are going to switch to manual mode first just to test the process. To change to manual mode, I just need to click on the manual button. As you can see in the real-time monitor, the control mode has changed to manual. Now I am going to start the simulation by clicking on the Run button. As we can see here, the process variable is 25 Celsius, the minimum value, because the manual output control is 0. Now let's move the manual output control to 100%. By doing this, we are driving the input of the process to 100%. In other words, we are fully opening the gas valve. We can see that the process variable is now going up, and at some point, it should settle at its maximum value, which is 300 Celsius. Now the output is 300 Celsius. Let's try a value in the middle. I will set the manual output control to 50%. That means that we are driving the input of the process to 50%. In other words, the gas valve is 50% open. The output should settle at the middle point between 25 and 300, which is 162.5 Celsius. As we can see, the process is behaving as expected. Now it is time to test the system in automatic mode. Remember, in automatic mode we no longer have direct control over the input of the process. In automatic mode, the PID equation controls the input of the process to drive the temperature to the desired set point value. Before switching the system to automatic mode, I will drive the input of the process to a low value, let's say 15%. Now let's wait for the system to settle. Now, I'm going to enter a set point value, let's say 160 degrees. As you can see, the set point is now at 160, but the process variable is not moving because the system is in manual mode, so the controller ignores the set point. Before switching to automatic mode, I need to enter some tuning parameters. I am going to enter 1.4 as proportional constant, 0.2 as integral constant, and 0 as derivative constant. So, this is a PI controller with no derivative action. Now that the process variable has settled at around 66 Celsius, and the set point is in 160 Celsius, I am going to switch the system to automatic mode by pressing the auto button. At that moment, the PID controller should start driving the process variable from its current value of 66 Celsius to the target set point value of 160 Celsius. We can see now that the process variable is increasing, it overshoots a bit the set point, and decreasing again. These tuning parameters are by no means the optimal ones. We can see that there is overshoot in some oscillations, but at the end the process variable settles at the set point. Now I am going to make another set point change. Let us enter a set point of 80 Celsius. We can see that there is a little bit of oscillation, and finally the process variable settles at the new set point value. Let us try more set point changes to verify that the simulation is working properly. And this was the basics on how to use SimuLoop. Thank you for watching.